All right, here we go. This is an example of Gauss's law with a conducting shell surrounding an insulator. In this particular case, the insulator has a charge density rho equal 4r, and the outer conductor, we just say it's got a charge -2 plunked right on top of it. So all of these problems are solved the same way. You have to find the electric field everywhere, and you got to do that by breaking it up into chunks, okay? So the first thing you do is you want R less than A. Okay, so note that I drew this little sphere. It has a radius less than the big radius. This is just the surface that I want to find the flux through in order to find the electric field. So the first step is we write down Gauss's law. We always write integral of E dot dA is Q enclosed over epsilon naught. What's Q enclosed? It's the portion of all of this charge that is inside of this sphere. So obviously it's not all of it, it's just the chunk that's inside that sphere. If we want to calculate that, then we need to integrate over the volume of that Gaussian sphere. So just to be clear, this dV here, this refers to the volume of our Gaussian surface, not the volume of the insulator, okay? Now, I was able to take E outside the integral here because of all those nice symmetry arguments that we've been making over and over again, that the electric field is constant on that Gaussian surface. In fact, that's why I picked a sphere in the first place, is a sphere has the same kind of symmetry as my charge distribution. So the left hand ends up becoming EA. On the right side, here's rho. And dV is 4 pi r squared dr. Now, if you're fancier and you've had Calc 3 before, you probably know that dV is r squared sine theta dr d theta d phi. That's in spherical coordinates. But the truth is that our charge distribution doesn't depend on theta or phi, and all of that ends up becoming the 4 pi there. Another way to see this physically is you're kind of building this volume by making lots of shells. Each shell has a volume of 4 pi r squared and some thickness dr. So 4 pi r squared dr is indeed the volume. At any rate, that's just some integral. We do the integral, we end up with that. So on the left, 4 pi r squared, that's the surface area of my Gaussian sphere. Okay, and on the right, you've got a volume times the charge density, so that's the charge, and then electric field ends up looking something like that. And this is not a particularly significant result. I chose the charge density at random just as an example to show you the kind of thing you can do, but at any rate, that's that. So let's collect that over on the left. We're done with R less than A. So the value of the electric field, it'll always point outward, right? It'll always point outward. The value of the electric field, so long as we are inside the insulator, is that. Okay, notice it gets bigger as you get toward the edge of the insulator. Okay, so the next region, now we want to be between A and B. So that's what this guy's telling us here. R is between A and B. I've done the same thing. I've drawn another sphere. This time the sphere is bigger than the insulator because that's the region I'm in. And my approach to this problem is exactly the same as my approach to the last problem. I'm going to write the integral of E dot dA equals Q enclosed over epsilon naught. I'm going to pull the E outside of the integral, as I always do because of symmetry. I'm going to re-express Q enclosed as density times volume. And now here's the only thing I'm going to do differently. This is the exact same integral I wrote before, except for one thing. I'm going to go to A instead of going to R. And here's the reason why I'm going to do that. Technically, I should go all the way from 0 to R. But my charge stops at A. In other words, if I were going to do the integral from 0 to R, that's the same thing as the integral from 0 to A plus the integral from A to R. But the thing is, in both these regions, if I'm finding the total charge, rho in this region is 0. I don't have to bother with it. In other words, there's no charge here. It's all 0, 0, 0, 0. So there's no point in including this part of that integral. So I only need to go 0 to A, and that's in fact why I've set the integral up that way. Otherwise, the rest of it goes exactly the same way. This is even the same integral. I just plugged in A instead of R. Only now, when I solve for E, I end up with something that looks like this. Okay, now I've rewritten it a little bit differently. So 4 pi a to the fourth, I'm calling that Q total because that's everything. That's all there is inside of this insulating shell. And I wanted to make the point that once you're outside of the insulating shell, even though you did all this hard work and it's kind of a crazy setup, this just looks like a point charge. In other words, if all you had was an electric field sniffer and you were blind, the electric field sniffer would say, hey, did you know that there's a point charge sitting at the origin that has a total charge, Q total? And that's all that's going on here. That's all you can see. So that's why I express it as Q total. You don't have to. You could leave it as 4 pi a to the fourth if you want, but I called it Q total just so you could see this looks just like a point charge. Okay, let's park that. Okay, so that's for R less than B but bigger than A. Okay, so the next thing we want to look at is inside the conductor. So that means that R is between B and C. And so this one is actually really easy because the key word here is conductor. Inside of a conductor, the electric field is zero. There's nothing to calculate. We know that the electric field has to be zero inside of a conductor because if the electric field weren't zero, all these little charges that are allowed to move inside a conductor would start moving, and they'd continue to move until the electric field was zero. In other words, they'd move around until their electric fields balance the electric field that's there already, and you'd end up with an electric field of zero. If you're skeptical of this and you're like, how do we know that the field will actually be balanced? Well, experimentally, I can tell you that if you take a voltmeter and you put it on two pieces of the same conductor, you'll always measure a voltage difference of zero, which means that there's no electric field inside of a conductor. This really does happen. There is a little bit of time that it takes for the charge to kind of sort out where it wants to move, but that is extremely small period of time, and we're interested in after that's happened. So we're in electrostatics, okay? At any rate, the electric field is zero, but there's actually more to say here. We could talk about how much charge. I said the conductor rearranges its charge. Well, let's figure out how its charge gets rearranged. I know that I have minus 2q total, but where does that live? Okay, so we're going to do the same thing we did before. We're going to write integral of E dot dA equals Q enclosed over epsilon naught, only this time the left side is zero. I know it's zero because the electric field is zero, but that means that Q enclosed has to be zero. But how could Q enclosed possibly be zero? I have all of this charge. This is not zero charge. So somehow this conductor needs to cancel off that charge, and that is exactly what it will do. If I have Q total here, the conductor will send a bunch of electrons to this inner surface, and those electrons will all add up to minus Q total. That way, if I look inside my sphere, I have zero net charge. That is how conductors create no electric field inside of them. So that's how much charge is on the inner surface. And then if I want to know how much charge is on the outer surface, well, I know that the total charge is minus 2Q. And so Q on the outer surface is the total charge minus the charge on the inner surface. So the minus turns into a plus when you minus it. And that's on the outer surface. More than that, though, typically these problems want to know what the surface charge density is. And I'll explain why that's important at the very end. But if we wanted to find that, well, surface charge density, that's just Q over A. And so for the inner, you use the inner surface. For the outer, you use the outer surface, and you get stuff that looks like that. I'm going to park that over on the left, too. Okay? All right. Last region we want to look at is outside of everything. Okay, so we make a surface, the surface encloses absolutely everything, and now we're experts at this. So this is for C less than R. We set up the same thing we did before. E looks like 4 pi R squared E, only now, look at this. Writing the charge is easy. I know that the conductor has a total charge of minus 2Q. Never mind how it's distributed. That's how much charge there is, and it's inside my surface. I know that this guy has a total charge of Q total. Never mind how it's distributed. I know that that's also inside my surface. So I add up those two charges, then I divide by 4 pi R squared, and guess what? It's another point charge. It's another point charge. Once you get outside of the conductor, your little electric field sniffer thinks that you have a point charge sitting at the origin with this much charge on it, and it's creating that electric field. So all the information gets hidden about what's actually going on. So that's how you find the electric field in all the regions. Okay, and we've also found the surface charge densities. So just 2 points I want to make really quickly. Number one, if you look at the electric field right near the conductor's surface, like right here and right here, you'll see if you plug in R equals C and R equals B for this surface, you'll see that the electric field is actually equal to sigma over epsilon naught near the conductor's surface. And that is not a coincidence. When you get really close to the conductor's surface, it looks like an infinite sheet. And if you remember, the electric field due to an infinite sheet looks like sigma over epsilon naught. Technically, it looks like sigma over 2 epsilon naught if you have both sides. But the point I'm making is it's not surprising that the electric field looks like the electric field from an infinite sheet when you are very, very close to these things. Okay. The other point I wanted to make, this is a weirder thing. I wanted to just show you a graph of what the electric field looks like, just to show you some things that it does. The first thing is when R is less than big R, so right here, this is inside, the electric field increases. Now, this increases like R squared. There's nothing fundamental about that. That has to do with the charge distribution I picked. But what is fundamental is that the electric field is increasing. And that is typical. When you are inside of a charge distribution, the electric field will increase as you get farther out. And that's because the farther out you get, the more charge you see, and the electric field will actually look stronger. Once you get outside of the charge, now you're getting farther away from all the charge, and it looks just like a point charge that you get farther away from. And then here's the really weird thing that happens. You come to a conductor, and this is not a well-behaved function. These are discontinuities. The electric field goes from here to 0 instantaneously. So this is a discontinuity. The electric field is discontinuous across surface charges on a conductor. And this is not a mistake. This is actually the way that these things work. And then you notice that once you leave the conductor, it picks right back up and it becomes a point charge again, falling off like 1 over R squared. So the fact that this is R squared is not super fundamental. Again, it depends on what we picked for rho. What is fundamental is that it increases and then it decreases, and then inside the conductor it's 0, and then outside the conductor we pick back up with the electric field of a point charge. Okay, hopefully this was more helpful than confusing.